the cloud has a greater carbon footprint than the airline industry, which is surprising because all of us take planes fairly regularly, commonly enough, and we're aware of this impact. But with AI, it's a lot more intangible, and even the definition of the cloud is quite intangible, and it's really hard to imagine that a cloud has a carbon footprint. Like, what does that even mean? So let's start with the origins of AI. I actually love starting here because I know that for a lot of people, AI as a societal phenomenon has started maybe with ChatGPT a couple of years ago, but actually there's a lot more to it than that, and we can go back a lot further. And actually, interestingly enough, we can go back to Alan Turing, very, very apropos. In 1950, he asked this question of what it takes to make, what it would take to make machines think. Can machines think? How can we do that? And this was really the spark that started artificial intelligence as a field. And it's interesting because after that, it became, it wasn't actually named artificial intelligence until about 6 years after. There was this convening at Dartmouth College, and people came together, and it was philosophers and psychologists and the first computer scientists or mathematicians, and they coined this term of artificial intelligence, and it continues to this day, and we continue working on this legacy that started with the brilliant Turing. So there's this one very mythical paper. It's called "Attention is All You Need," that was published out of Google, actually, and it really laid the foundation of what we currently use in most of our interactions with AI, so large language models like ChatGPT. It created this building block of large language models called a transformer. And then this was built upon by other papers that tried to go further about how much data do you need to train a model, how much compute, so how many, computers for how long is needed, how big does the model itself have to be. So there are all these like scaling laws and compute optimal formulas that were defined over the years, and so a certain ideology, if you may, and in most recent years, I guess, once the technology left the academic lab and hit industry labs and hit actual systems that are being used today, it's hard to sum up in a single sentence, but if you may, I found this T-shirt and I found that was really quite emblematic. So scale is all you need. That's the first one. So more data, bigger models, more compute. That's going to solve whatever you want to solve. And the second part is AGI. So artificial general intelligence is coming. So AI is going to come and solve all of your problems as long as you use enough data for a big enough model and train it for long enough. That's the magical formula. You got it. Like, it's going to solve all the problems. And so this brings me to the second part of my presentation, the consequences of scale. So essentially, now that we have these foundations of AI, we have this machine learning approach, now it's been really translated into bigger is better, scale is all you need, and this definitely comes with consequences. So let's start with what I work on most these days. Environmental impacts. So probably you've seen headlines such as these ones around environmental impacts. So water, energy, greenhouse gases. It seems to be pretty common on the news nowadays to read these headlines and on different aspects of environmental impacts around the world. Right? This has really become a phenomenon that's pretty global at this point. And so it's widely said that the cloud has a greater carbon footprint than the airline industry, which is surprising because all of us take planes fairly regularly, commonly enough, and we're aware of this impact. But with AI, it's a lot more intangible, and even the definition of the cloud is quite intangible, and it's really hard to imagine that a cloud has a carbon footprint. Like, what does that even mean? I guess the etymology is a separate issue, but these impacts are really growing. But how do you translate this this global number into very specific actions, right? Very specific tools that we use. Well, what do we know about the carbon footprint of using ChatGPT? There are, let's say, conflicting numbers and conflicting opinions about how much that really represents. And we did a study with this with some of my co-authors 2 years ago now, and we looked at all the most popular models that people used in practice, so notable AI models, and we looked at how transparent they were about their environmental impact. So how much energy they used for training, even how much compute they needed, how much carbon they emitted. And we noticed that, I mean, there was a slight peak in the 2022, 2023 pre-ChatGPT period, but largely speaking, the red has been pretty prevalent. We have almost no information about these models, and these are the models that we interact with every day, mind you. We have almost no information about their carbon footprint. Now, what's interesting is that maybe some of you have seen some numbers floating around. Usually at this point, people are like, but how about this number, for example, that I saw from Sam Altman on his blog in June 2025. So he did post something along the lines of the average query of ChatGPT uses 0.34 watt hours and compared it and blah, blah, blah. The thing is, we don't know where this number comes from. We don't know what an average query represents. We don't know what the methodology is. Hasn't been validated. We truly don't know. And so, for example, often people are like, oh, well, that's an LED light bulb for a couple of minutes. It's probably not that bad. Maybe, but also we don't know how what this actually represented to begin with, but also how that's shifted with the ways that we use AI nowadays. We're kind of stumbling around in the dark when it comes to environmental impacts of the systems that we use every day. What we do know, though, is that the cost of training AI models is growing. So between 2017 and 2023, often AI labs will publish how much, what dollar amount of compute they used. And just based on these numbers, we see a very exponential growth in training time, so how long it takes for a model to, for example, learn what it's trained to do. This could be a proxy for energy, potentially, but all we know is that it's getting more and more expensive to train these systems. That means there's less and less organizations, people, what have you, countries that can actually participate. We do have some numbers about data centers as well. What we know is that data centers around the world have their energy use has doubled since 2020, in the last 5 years, pretty much, and it's set to double again in the next 5 years. So we know that, generally speaking, it's getting problematic. It's getting noticeable as environmental impacts, but of course it's really hard to say which portion of this is AI specifically, and that's often the debate. Like, sure, data centers, but how about Netflix? Like, sure, data centers, how about the web, right? So it's really hard to say what portion of this is AI. What we do know is that AI companies are largely driving this race to building more and more data centers. So, for example, the Stargate data center in the United States is absolutely colossal. Like, those tiny dots are cars on this image. And OpenAI recently announced that their first phase, and once operational, once fully functional, it's set to generate about 3.7 million tons of CO2 per year. This is as much as the whole country of Iceland for a single data center. Now, another aspect that often gets brought up is water. And there's this rather iconic, infamous, or famous statistic that you might have seen that haunts my dreams about 500 milliliters of water. Once I was at the theater with a friend, and it was a play about AI in Montreal, where I'm from, and then they started opening bottles of water and dumping them into a garbage can, and I had heart palpitations because this is every time you talk to ChatGPT, it's a bottle of water. It's more complicated than that. Once again, it's really hard to get information, sadly, but there's different aspects of this in terms of water usage. So, for example, there's the actual cooling. If you ever get a chance to visit a data center, niche, I know, take it. It's actually very interesting. These things are massive, and they get very, very, very hot, especially nowadays with AI. The computer servers that they use are very dense. It's I don't know if anyone remembers PCs, before laptops. So it's like that, but more, bigger, hotter. And so they really need to pipe cool water through the infrastructure in order to cool it down constantly. Otherwise, they overheat. And so there's the cooling aspect. And so that's definitely one way that the water gets used. There's generating energy, and there's also creating these microchips that are predominantly used for training AI models. So GPUs, doesn't matter, graphical processing units, but essentially in order to make them, they put microscopic layers, and each layer has to be cleaned with ultra pure water. So even the factories in which they make these chips use tons of water. And of course, there are trade-offs to be made. So for example, you can either use the water and let it evaporate, which is kind of the cheapest and easiest way, but of course you're using a huge quantity of water, so 70 to 80% of that water that you use for cooling, for example, would evaporate. In other cases, you can do a closed circuit and the water will just circulate, but of course it heats up and you have to cool it back down again. And how do you do that? Well, you use more energy. So often there's not really any like win in terms of energy or water trade-off. And in fact, as these data centers get built out more and more, the tension really becomes apparent. So for example, 2/3 of the data centers built in the recent 4 years are located in regions that are already water stressed. I mean, the UN, I think 10 years ago or something, already declared that water is the next big environmental tension worldwide. Well, data centers are making this more apparent, because essentially once they get built, for example, if they use evaporative cooling, they're pumping water out of the soil, out of aquifers locally. And that means that in places where it's already a strain, where there's already droughts, where there's already a lack of water, then that can make it even worse. How do you compare humans and AI in terms of environmental impacts? And there's actually the study that came out that tried to answer this question in 2024. And it's pretty interesting, because what they did is, what particularly irks me, is that they took a study that I led about Bloom, a large language model, and we did some estimates of how much energy and carbon it takes to query this model. They compared it to the random number that Sam Altman shared, and they also took the average carbon footprint of a human being in the United States and India, and divided it by the amount of time it would take roughly a human being to write a page of content, and compared the two. So this is like querying an AI model. This is a living, breathing human being that does other things, including writing. And they did the same thing for image generation, image creation. And their conclusion of the study was AI writing produces 130 to 1,500 times less CO2. So essentially, AI is better for the planet than humans. I'll let you continue that thought further. And same thing for AI image creation. So once again, 300 to 3,000 times less CO2 than per image, less than human creators. So essentially the conclusion of this study is that we don't need human authors. I mean, if we want to truly be good for the planet, we don't need human authors, we don't need human illustrators. We can just replace them all with AI and we'll be better off. And so this was really making the rounds and getting kind of shared by some very respected people in the AI industry. And then I read it, and of course I have a lot of opinions, but also I found this footnote that said, emissions analyses do not account for social impacts such as professional displacement, legality, and rebound effects. So we'll go back to rebound effects in a second, but just to show you that it's really hard to say, X is better than Y, humans are more or less sustainable. These kinds of comparisons are very tricky and get very ethically dubious quite quickly. And so I don't think this should be a focus, and I don't think this should be our main question. I think our main question should be, how do we think about these impacts? How do we quantify them? How do we reduce them, instead of being well, let's just replace a bunch of human authors with some AI. Another aspect that I think we don't think a lot about is how it's impacting our way of thinking and kind of reasoning and our cognitive skills in general. So for example, when's the last time that you opened a cookbook or a map? I was talking to my kids about this the other day. They were like, no, only pirates use maps. And I'm like, no, I swear. About 15 years ago, we used to use maps. So nowadays, I mean, we're doing a lot of cognitive offloading in the psychological sense, that instead of thinking about something or, just improvising in the kitchen or getting lost on our commute or, taking a different route, we're going to be really using our phones or technology as a crutch. And, even for example, phone numbers. How many of us remember any phone numbers by heart, or birthdays, right? We have this cognitive offloading that we're doing more and more, and as better as the systems become, the more and more things we can do, right? And so, for example, now you can take a picture of your fridge, and then it's going to generate, ChatGPT or whatever can generate a recipe for you. So you don't even need to think anymore. You can just go to the grocery store, and then it's going to generate a grocery list of stuff to buy that you're missing, and then after that you have a meal plan, and after that, you don't even have to think at all. But there's this recent research from MIT that's called Your Brain on ChatGPT that compared people that were writing essays by themselves and using large language models, so ChatGPT, and they actually found that the neural pathways, the neural connectivity of these different groups was different fundamentally, and that the cognitive strategies used were different. And then over time, it was like over several months, brain connectivity actually decreased in people who were systematically using ChatGPT for writing essays. And so there was another study that was done a bit more recently about rebound effects. I said we'd come back to rebound effects caused by AI, both at work and at home. And they found that, so even though the effects of automation at home and in the industry are different, in the end, they both lead to more resource consumption and environmental pollution, because essentially people will buy more stuff or travel more or actually like do more detours and things like that because now they have more time. Their commute takes them less time rather. And so it's interesting because these things of like, of course AI saves us time, of course tech saves us time, but what happens with the time that we save? And this brings me to a very interesting paradox that was actually coined in the late 19th century called Jevons paradox. And Jevons was an economist, and he observed this with coal. And essentially he found that Jevons paradox is said to occur when technological progress increases the efficiency with which a resource is used, so we could generate more energy for the same amount of coal, but the falling cost of this use induces increases in demand enough that the resource use overall is increased and not decreased. So essentially, we've gotten better at using coal, so we can go like further, or generate more energy with the same amount of coal, but we actually end up using more coal overall because we're using it in more and more things and using it to power a whole industrial revolution. And the same thing happens with cars. So for example, cars are getting more and more efficient, so now with the same amount of fuel, you can go further, and so now we're like, well, why don't I drive somewhere for the weekend, right? Why don't I go further? Why don't I use my car for X and Y? I have the set budget that I can use, and it actually ends up causing, more pollution, more traffic, more fuel use. And this is a paradox because, technically our cars have been getting more efficient for a while now, so we should, pollution should be going down, not up, right? But it actually is going up. And there's a similar observation. I mean, this is the CEO of Microsoft that tweeted this, saying that, well, AI has a Jevons paradox. And it's true because if you think about it, we're getting more and more bang for our buck. Like we can do more and more things with AI, but we're also using AI in more and more things. And so at the end of the day, if you think about it from a macro perspective, the impacts are actually increasing and not decreasing. So, if you focus on just like the efficiency, you can be like, yeah, but nowadays with, I don't know, $1 or $100 for an AI tool, I can do so much more. Yeah, but you're using it so much more as well. And so this whole paradox is a very interesting way of thinking about rebound effects and how we interact with AI in society. How do we actually measure these impacts? Well, this is kind of where my whole research career in this field started, and I helped create a tool called CodeCarbon. So if any of you are AI model developers or programmers, please use it. The goal is really to measure from a device perspective, like on your computer, how much energy it's using, and based on your IP address, for example, where that energy is coming from, how it's generated. Depending on where you live, energy is generated in different ways. Sometimes it's renewable, sometimes it's less renewable, etc. So it uses those numbers, and it gives you equivalents. So for example, it can compare it to miles driven by a car or household emissions and things like that. So really the goal is to improve transparency in the field and to give us more information about how much, what the environmental impact of AI is. Another thing that's not all bad, that's quite good about AI, is the AI for climate work that's being done. Also here at the Turing Institute, there's some really, really great work that's being done in applying AI for climate-related issues, problems that we have. The thing is with climate change, it's not like a single problem we have to solve. It's like thousands of problems that we have to solve, and each one of them, maybe some portion of it can be solved using AI. It's rarely like the solution, but it can definitely be part of the solution. So for example, everything from designing new batteries. So we know we need to electrify our systems, but we know that lithium-ion batteries are not ideal, right? They're not perfect, so there's new batteries that can be designed with AI. There's all sorts of ecosystem monitoring that can be done because AI is really good at analyzing lots of data, and also at a meta level, like predicting the weather, detecting methane leaks from space, monitoring coral reefs. There's all this remote sensing, it's called, data that's gathered by satellites that can be used with AI. So there's some really great work being done there, and a lot of this doesn't involve any kind of generative models. It's often pretty simple models that are very domain specific, that are trained on that data, that are not gonna help you plan your vacation in Italy and predict the weather. No, they're only going to predict the weather, and they, are created by domain experts. They don't need a lot of computational resources, and they do a really great job at the tasks they're meant to do. One of my favorite examples of this is Rainforest Connection, and it's like a nonprofit tech lab in California. And what they do is they take old cell phones and they do bioacoustic monitoring of the Amazon rainforest. Essentially, they can detect illegal logging just based on the sounds that like the chainsaws and the trucks and the humans make. And it's like anomaly detection, essentially. It's like, well, this is a parrot, this is rain, this is whatever, this is a monkey, and this is a chainsaw. So that's an anomaly. And they work hand in hand with rangers, and they send the rangers in order to stop the illegal logging, because it usually happens in a very kind of ad hoc way. And so this is an example, like they're not using cloud servers, they're using old cell phones, right? We can do really great things with a smaller amount of compute, and if we think about the problem more. There are also regulatory solutions. It might look bleak in the United States currently. There was an executive order that essentially removed a lot of red tape in terms of environmental protection for data centers specifically. That was signed in July of last year. So that could look bleak on a federal level. I know a lot of people are kind of like, well, you know, the damage is done. But if you look at it at a state level in the United States, there are a lot of states that have local regulation when it comes to data centers. And so they essentially are trying to put safeguards in place. Because if you think about it from like kind of a regulatory perspective, the benefits of building a new data center are global. Like anyone can, query it, can run a model. Even here in the UK, you can use a data center in Virginia, and actually a lot of, something like 85% of the web traffic globally is out of the eastern US. And so like when you build a new data center, you add more capacity, it benefits everyone, but the impacts are very, very local. So the impacts in terms of energy, in terms of water, in terms of pollution, as we saw. So essentially it's a trade-off for governments to figure out like how they want, like who's going to pay the bill for the local impacts. Historically, they've just been giving them tax breaks. Like in the last decades, it's like you want to build a data center, cool, you don't need to pay taxes for 5 years. But nowadays, they're thinking about how you can actually protect the local population, which is really great. In the EU AI Act, you do have some energy efficiency requirements. They're mostly voluntary for now, but we do have the Energy Efficiency Directive, Taxonomy Assessment Framework, and one that I'm particularly hopeful about are standards. And I've gotten really into standards lately because I think that they're a very tractable way for us to understand the environmental impacts and for regulators to kind of make laws, because it's really abstract for a lot of people, like kilowatt hours or these very like joules or whatever, like what even is a joule? But if you have these labels, whether it be for appliances or apartments, right, you kind of get it that this one is better than this one. And so a couple of years ago now, we asked this question about light bulbs have efficiency ratings, why can't AI chatbots? And a bunch of us came together and we wrote this paper in Nature. And then this became kind of the genesis of a project called AI Energy Score. And so the goal of AI Energy Score is we tested hundreds of open source AI models. So those are the ones like, for example, the DeepSeek model, which you could download and run locally. And then we used CodeCarbon, which I told you about, to measure the energy. And what's interesting about AI is that it's not a single thing. Like there's not one single thing that you want to do with AI. And so there's lots of different models that exist. Some of them are very simple and very efficient, and some of them are very big and consume a lot of energy. And so, for example, if you're doing something simple like classifying a movie review, is this a good movie or a bad movie? And you have a bunch of people who said, oh, this was really crappy or this was amazing. You don't need a large language model for that. You can have a very simple text classification model that will use hardly any energy that can do the task very well. And if you have, if you're generating a high quality image or video, you need a very intensive, energy intensive model for that. And so we tested all of these models across different tasks, and we assigned them scores essentially. And so this is comparison of two models for text generation. And so you have one that uses, once again, abstract numbers, but 5 watt hours for 1,000 queries, and you have one that uses almost 20 watt hours for the same amount of queries. So you see that the difference is, significant, almost 4 times more. But you can just ignore that and look at the stars, and you know that 5 stars is a better model. And so essentially focusing on ratings like this, then of course this is not like a global thing. It's not going to solve everyone's evaluation issues, but essentially what this can do is inform policymakers so that you can regulate and say, well, if you have a model that is always on and queried by, whatever, 1 billion people a day, like you have for a lot of these AI models, it has to be a 5-star model because it's always on. If you have a model that's, predicting the weather and running once a day, then it can use more energy. But like you have this granularity and you can use these energy scores to compare the different models. And just somewhat of a conclusion, I know we're pretty much at time. I know that for a long time, so going back a little bit, before I started doing this work, I was working in, just applied AI research, and I was having more and more kind of like climate anxiety and worried about the climate. And I felt that there's so many things I can't control. Like, sure, I can stop flying, I can stop eating meat, but still at the end of the day, there are these big structural things. And then I quit my job, I started doing my research. I mean, it's somewhat better now. I am here, but it also helps to understand these processes and these systems and these structures, and it's hopefully something that you'll take away today, that it's not, AI isn't magic, it's not ephemeral, it's not this mythical cloud. It actually has a very physical component, and this physical component has impacts on our environments, and the way that in which it's used has impact on our societies and our economies. So it is very tangible, and something that irks me a lot about the discourse on AI nowadays is like, oh, well, it's too late. Well, the genie is out of the bottle, the toothpaste is out of the tube, it's too late, it's happening, embrace it, use ChatGPT to generate your recipes and, bedtime stories for your kids, like, let's move on. I disagree with that fundamentally. I don't think anything is a done deal, and there are definitely ways of shoving toothpaste back in a tube, by the way. So I do think that there are things that we can do, some of which I've talked about today, and I know that not everyone is an AI developer, but a lot of us, most of us at this point, are AI users, and as users, we can definitely contribute by making these small gestures and thinking about the way in which we engage with AI. And something that I think about a lot when I think about sustainability is this definition of sustainability that kind of got forgotten over the years, unless you really work in the field, that something isn't sustainable just because it's environmentally friendly. Something is not sustainable just because it's equitable, just because it's from a social perspective, and it's not sustainable just because it's economically viable. That it's really this intersection of these three pillars of sustainability that makes something truly sustainable. And so nowadays, I mean, you saw the themes that I spoke about. I try to really think about how can we find ways of using AI or types of AI to use that cover all three of these pillars and think about it a little bit more holistically. So hopefully this is something that you'll bring with you tonight. Thank you very much.